This video focuses on sections 13.8 and 13.10, the preparation of epoxides and reactions of epoxides. Remember from Organic 1 that you can form an epoxide using a peroxy acid, and a peroxy acid is one in which you have two oxygens next to each other in what would otherwise be a carboxylic acid if there were only one oxygen in the blue highlighted portion. The mechanism for this reaction is concerted. We have 4 reaction mechanistic arrows to get through in order to accomplish this concerted reaction. Examples of peroxy acids are metachloropurbenzoic acid and peroxyacetic acid. Again, we're looking for this OO bond in what would otherwise be a carboxylic acid. The second way that we can form epoxides is with halohydrin formation. First, we're going to treat our molecule with bromine and water to form the halohydrin. This goes through an intermediate where we have the bromonium ion. And in the next step of this mechanism, water attacks to break the carbon-bromine bond, giving us this intermediate where our substituents are trans to one another. Once we add sodium hydroxide, we deprotonate this alcohol, giving us the alkoxide. And that alkoxide can then undergo an SN2 reaction with its neighboring carbon. And it kicks out the bromine as a good leaving group and forms the epoxide ring. Note that it's important that groups in cyclohexane rings must be trans to one another for this reaction to work. But what if they aren't? Let's take a look at this example where we have the hydroxy group and the bromine atom cis to one another. Here in our first step with sodium hydroxide, the alcohol is deprotonated to form the alkoxide, but no intermolecular reaction occurs next because the alkoxide and the bromide are in the wrong positions to undergo SN2 reactions. The only other possibility is that this molecule encounters another equivalent of itself, which it's likely to do, and here we have a proton that is trans to our bromine atom. So our alkoxide can take that proton, form a pi bond, and bromine is removed as a leaving group, forming our neutral halohydrin and an alkene. Be careful with the stereochemistry of your products. Notice that when you're adding MCPBA across a pi bond or when you're forming a halohydrin, you want to put them on the same side of the pi bond. So imagine that this molecule is in the plane of the paper and the MCPBA is above it. It's going to add to one side of that pi bond or the other side to form the enantiomer. Next, we move to section 13.10, where we talk about the ring opening of epoxides. Epoxides open when they are treated with strong nucleophiles. An example is shown here in which epoxide is treated with sodium hydroxide and water, and it forms this diol. How does this work? We take hydroxide, which is our good nucleophile. It attacks the carbon of the epoxide ring, and the ring opens to form this deprotonated diol. This is in equilibrium with the water that's present. Protonation gives the neutral diol plus hydroxide. Here we have another instance where an alkoxide is a leaving group, and we discussed this in the reaction of Grignard reagents with esters and reducing agents, lithium aluminum hydride with esters. And in this case, we have an alkoxide leaving group, even though it's not a good leaving group, because the bonds are so strained in the epoxide that the carbon-oxygen bonds are weaker, and that allows for the alkoxide to form. Be careful with stereochemistry in epoxide ring opening too. If we look at this first example, it's attacking the carbon on the right. And so we get an inversion of stereochemistry at this carbon in yellow, which means we need to flip these R3 and R4 to go up, and the hydroxide is at the bottom. That gives us our inversion of stereochemistry. And the same thing for the molecule on the right. We get an inversion of stereochemistry at that leftmost carbon atom. Now let's ask a question. What happens if the epoxide is asymmetrically substituted? Here we've got a methyl group on one side and protons on the other, and we wonder what the nucleophile is going to do. The nucleophile is going to attack the less substituted carbon when it opens the ring. And the reason that it does that it attacks the less substituted carbon, is due to steric hindrance. You would expect this to be the case for an SN2 reaction. Many nucleophiles can attack epoxides. We have esters, the alkoxides. We have alkoxides, cyanide, the deprotonated thiols, Grignard reagents, lithium aluminum hydride are just some of the nucleophiles that can attack epoxides. And these are all under basic conditions. But we can also open the epoxide ring in acid-catalyzed conditions. Here, when we treat our simplest epoxide with the hydronium ion, we get the same product as we did when we treated it with sodium hydroxide. But the mechanism here is different. Given that we've got a strong acid, the first thing we want to consider is protonation of the epoxide alcohol to form this protonated compound, this protonated cation. Then, in a second step, water attacks. And opens that carbon-oxygen bond. In a final step, we use a molecule of water to deprotonate that cation, giving us our diol plus the hydronium cation. Recall that in the treatment of sodium hydroxide, the hydroxide attacked the less substituted carbon atom, but in acidic conditions, it turns out that the nucleophile attacks the more substituted carbon atom. So let me highlight which atom is attacked in each case. So on the left, we've got the less substituted carbon atom being attacked, and on the right, we've got the more substituted carbon atom being attacked. Now, when we're treating with sodium hydroxide or hydronium, I can't prove this to you. We have to use a different nucleophile in order to demonstrate that this happens. So let's use methoxide and protonated methanol to look at this difference. In one case, we are attacking the carbon on the left, we're attacking the carbon on the right, which was the less substituted carbon. And in the second case, in acidic conditions, we're attacking the more substituted carbon. Why does this product form in acidic conditions when the nucleophile attacks the more substituted carbon? The mechanism helps explain what's going on. First, we get a protonation of the epoxide oxygen forming this cationic intermediate. And what we need to know about this cationic intermediate is that it's positively charged, but that positive charge is spread over the epoxide ring. So we have a positive charge partially at the carbon atom on the left and the carbon atom on the right. Both of them bear partial positive charges. But we know that from understanding carbocation stability, the more substituted a carbon is, the more stable the carbocation is. Thus, more partial positive character can be found on the carbon on the left, which is more substituted. That makes this carbon a better electrophile and the one that is attacked by a nucleophile. Let's do a practice problem. Draw the mechanism and the product of the following reaction. So I want everyone to pause your video and see if you can work out the mechanism for this reaction and draw the product. And when you are finished, then press play again. Our first step is protonation of the epoxide. When considering which carbon bears more partial positive charge, it's the one in green that is more substituted. Then in a second step, we attack that more substituted carbon and then break the epoxide ring open. And now we're left with an alkoxide that's protonated actually. And we have to invert our stereochemistry at the carbon that was attacked. Our ether is protonated, so we need to use another molecule of methanol to abstract that proton. And that gives us this product. That's all I have for you today, and that winds up chapter 13. The next thing we'll do is have a video for a group workday exercise. We're not actually going to have a group workday, but I'll give you the exercises to work through, and I will provide a video to go through the solutions.